So before we get into the nitty-gritty of local extrema, I do want to do a quick summary of where we're at here and remind you of some stuff from algebra that when you had a function, you talked about some important points on it. And one of those things was the y-intercept. Where does the function cross the y-axis? And you can always get that by just plugging 0 into the function. It's always going to give you the y-intercept. And something else you did in algebra is you found the x-intercepts. So this one has 3 here where it crosses the x-axis. And the x-intercept's usually harder to get because you have to set the function equal to 0 and then try to solve for x. So that can be challenging at times. And these are important points. They still are, but this is something you learned in algebra. And what we're saying now with calculus is there are other important points now. And the other important points now are these extrema, these turning points. Calculus now gives us the power to figure out where these are and how high they are. And that's what we're doing now. We're now introducing you to, hey, here's some other important points on a function that we can now get with calculus. So to start, imagine 2 points. Any orientation you want, except right above each other. And we're going to connect these with a function. Has to be a function. And you can connect them however you want, as long as it's a function. And notice here that this endpoint is the lowest point of this function, and the turning point here would be the highest point. And this is true for however you connect these points. As long as it's a function that connects them, the extrema will always be the endpoints or these turning points. So just to be clear, we have 2 closed endpoints here, and we have 1 turning point, 2 turning points, 3 turning points, 4 turning points. So a local max, a local max, a local min, a local min. Those would be the local extrema. And the global, if we look, this endpoint is the highest endpoint of the function. So here's the global max. And if we look at this turning point, we see this is the global min, the absolute minimum point of this function. And if you are reading along in the book, they do mention a little bit about what's called the extreme value theorem in 4.1. And that is a proof that's saying all extrema are at endpoints or turning points. And remember, our ultimate goal here is to get all extrema, all global extrema, min max, and all local extrema, min and max. And these extrema are at endpoints or turning points. Now, for the most part, endpoints are pretty simple because they're simply given in the problem. So to get the endpoints, you just have to identify it from the problem. Most of the problems will give you the closed interval. If a problem doesn't give you an interval, then you're to assume it's the entire domain of the function. So how do we get these turning points then? So the endpoints, fairly straightforward. It's the turning points that are a little bit more of a challenge. And what we know about these turning points is they will always have a derivative of 0. So I got my slides a little bit out of order here. I'm just going to skip through that and go to this one. So at turning points, the derivative is 0. The derivative will be 0 there because that's what the tangent line will be, the slope of the tangent line. So that seems pretty cool. We just have to find where the derivative is 0 then. But it's not that straightforward. There is no straightforward way to get all extrema. There is a process. And one of the reasons there's a process is because if you look to the right, you can see this plateau also has a derivative of 0. So simply solving for the derivative equaling 0 does not guarantee you're getting an extrema point. You could get this plateau. So we can find turning points with the critical numbers that we talked about in the last lecture. We'll talk about more again here today. However, these critical numbers can also give us these plateaus. And there's nothing we can do about that. We just have to be aware of that when we're doing this calculation. We have to remember, hey, I'm getting these critical numbers. They don't guarantee an extrema because it could be this plateau. And we have to investigate that and then conclude what we're dealing with. And this is stuff we'll do, but I just want to lay it all out here in some words at the moment. So you may be thinking to yourself, well, okay, that's not too bad. All I have to do is find the derivative, which we're perfect at now, right? And once we have that derivative, we'll set it equal to 0 and simply solve. And then I just have to figure out if it's a plateau or not. And it is something we have to do, but it's not the whole story. Because what I have graphed here is what we would call a smooth function. And a smooth function means its derivative exists everywhere. And so when we go around this turning point, it's smooth. It's a nice curve there. The derivative exists everywhere. But a turning point could be sharp. So I want to show this picture that's in your book. And I really want to focus just on the top 3 here. None of the problems we're going to be dealing with have gaps. So like number 4 is gaps. We're not going to have any wild oscillations. But I do want to focus on these top 3. So they have 1 and 2. They call 1 a corner, 2 a cusp. I mean, that's fine. I like to, in general, just call these sharp corners. And the blue line is the function here. All these other lines are showing you the tangent. So the blue line here, and we come to a sharp corner, and then we go down again. And this is a turning point. And if we look over here at the cusp, again, it's the same thing. We're increasing positive derivative. We get to a turning point, and now it's decreasing. And so the thing I didn't talk about in the last lecture is that we can have sharp corners as well. And sharp corners is where the derivative will fail. And try to remember, I know it can kind of get lost in learning all these new things, but the derivative is a two-sided limit. And if the two-sided limit fails, then the derivative doesn't exist. And so at a sharp corner, the left-sided limit doesn't equal the right-sided limit, and so the derivative fails right at the sharp corner. And if you think about that, that gives us a way to find it. If we know the derivative will fail at sharp corners, then we can use that information to find these sharp corners. We will simply look for where the derivative fails. And so this is the next part, and this is the one that does pose a challenge for learning derivatives in calculus here, is we can also find these sharp corner turning points by looking where the derivative fails. However, a failure doesn't guarantee a turning point. And so we have to investigate. And this third picture here, a vertical tangent, this is where the slope is going straight up a vertical line, so a slope of infinity, you could say, even though technically we would say that doesn't exist. But a vertical tangent is also where the derivative fails. So we could be looking for where the derivative fails, and we might get a vertical tangent and not a turning point. And so again, we have to investigate. So it's the same thing deal. When we do the derivative equals 0, we have to investigate if we have a plateau or not. And then when we look for where the derivative fails, we again have to investigate to see if indeed we do have a sharp corner. And this is what we're going to do. So here's what we're going to do. Here's a summary of how we're going to approach this. Our goal is to find all turning points. Getting the endpoints will be straightforward. Just identify it from the problem. The challenge here is getting all the turning points. And how do we do that? Well, turning points will either be critical numbers or where the derivative fails. So that means the first thing we're going to do is solve for these critical numbers. Now I'm going to present this in a way that makes sense, and then I'm actually going to change the ordering. So I'm just going to keep going here for a moment. So the first thing we're going to do is solve for critical numbers. So that was this picture here. So we're going to solve for our critical numbers. And then we have to make sure that we're rejecting the plateau. So the plateau is a critical number, but it's not a turning point. Remember, that's our goal, to find all the turning points. So we solve our critical numbers, we reject any that are plateaus. And the next thing we've had to do is we had to then look for these sharp corners. We have to then investigate, okay, well, are any of my turning points a sharp corner? And we can do that by finding where the derivative fails, because the derivative will fail at a sharp corner. So we'll look for that failure. And for our problems, the derivative failures will mean division by 0 or some positive root of a negative number. So let's say you found the number 4 causes division by 0. So you plug 4 into your function, and that results in division by 0. What we need to do is we need to take that number 4. We need to take this number that caused failure and put it into the original function. If this failure number is in the domain of the original function, then we would also say this is a critical number. Now, this is the kind of logical flow there that I was hoping would make sense. And, oh, actually, there's one more thing I have to stick on here. Number 5. So once we found a failure number, now a failure could be a sharp corner, or it actually could be this vertical tangent here. A vertical tangent is not a turning point. So we'd have to also check that these new critical numbers that we're getting are sharp corners. So again, let me just say that. First thing we do, solve critical numbers. Part 2, reject the plateaus. Those aren't turning points. Step 3, we're going to look for where the derivative fails, because where the derivative fail could be a sharp corner. Once we find where the derivative fails, then we then have to check to make sure that failure is indeed a sharp corner. So this is the logic of what we're going to do, but the mathematical work that we actually do to get this isn't quite in this order, though. And the work we do to get this is we tend to solve for critical numbers first, and then we'll do step 3 and 4 next, is what tends to happen when we're doing the math work. So doing the math work, we'll get the critical numbers, and then we will check where the derivative fails. And then we'll check those failures to see if they're in the function. We'll then check the critical numbers to get rid of plateaus, and we'll then check the critical numbers to see if they're sharp corners. So this tends to be the order that the math work is done in. So, with all that said, let's do it. And let's start with a good old friendly parabola. Now, the book does ask you 2 questions here. The first one being find the intervals of where the function is increasing and decreasing. And the second part is find all extrema. Now, part A may seem a little bit intimidating at first, but part A is actually a natural process of working towards part B. So part A is really no big deal. We'll be doing this to get to part B. So what's the first thing we're going to do here? The first thing we're going to do is find the critical numbers. So we'll take the derivative. So we'll have minus 2x here, minus 3, and 0. So there's our derivative. And then we'll set it equal to 0. Because a derivative of 0 is where we'll have our horizontal tangents. And horizontal tangents are at turning points. And then we'll solve this. So we'll move to 3 to the other side. Divide both sides by the minus 2. And there's our answer. So there's our first critical number. Now the next thing to do is to check where the derivative fails. So here's our derivative. And remember here, failure means division by 0 or taking a positive root of a negative number. So if you look at the derivative, there's no division and there's no root. Thus, there's no failure. And we're done. Minus 3/2 is our only critical number. So what are we going to do with this? Now we're going to go back to something you may or may not have done in algebra. Is we're going to use just a number line. And this is what I would literally draw out on my paper, just some old number line here. And I'm just going to stick 3/2 on there somewhere. So we got minus 3/2 is our critical number. And I'm just going to say it's right there. The purpose of the number line here is literally your handwork. It doesn't have to look nice or anything. And this minus 3/2 splits this into two regions. We have the region that's to the left of minus 3/2, and we have the region that's to the right of minus 3/2. And I want to bring up this function again here. And notice, here's our first critical point for this function right here. And from minus infinity to the first turning point, we say the function is monotonic. Monotonic meaning it's entirely increasing or entirely decreasing. And so from minus infinity to the first turning point, the function is monotonically increasing. It's everywhere increasing. But notice what happens when we go to the next turning point. So if we go from this turning point here to the next turning point, the function again is monotonic, but now it's everywhere decreasing. And if we go from the middle turning point, the middle critical number to the next critical number, the function again is monotonically decreasing. And then from the last critical number to infinity, it's monotonically increasing. And why is this important? Well, imagine these three critical numbers I break into regions. So I'm going to put a region here. The other region will be the y-axis. And I'll have another region here at this other critical number. So I'm putting these lines where the critical numbers are. And so there's three regions here. I have this region, I have this region, and I have this region over here. Actually, these middle two regions here, the y-axis also splits this. And the point is, in these regions, the function is always doing one thing. It's either always increasing or always decreasing. And so what we're going to do is we're going to take our critical numbers and we're going to write it on a number line and break it into these regions, because we know the critical number is the only place where the function will change monotonically. In other words, the function isn't going to go to decreasing unless it goes through a critical point. I should technically say there it's for continuous functions. There is a case going into the future where you do have to worry about vertical asymptotes, but that is not in any of our homework problems. And I might have gotten a little off track there, but let me go back to this, what we're doing. We have our critical number. We're going to write it on a number line, and this splits the number line into two regions. And we know the function is doing only one thing in each of these regions. This left region, it's either increasing or decreasing, and same with the right. And what this means is we can pick any number we want in this region and test the derivative. So for instance, x equals 0 is in the region to the right. So what is the function doing over here? Well, we know the derivative. We know the derivative is minus 2x minus 3. And then what we're saying is, well, let's just plug in 0 because it's in this region. Well, if we plug in 0, we'll get minus 3. And what does that tell us? This tells us it must be sloping down, because a negative derivative will mean sloping down. And so we can conclude then that this entire region must be decreasing, because it's monotonic. The function is only going to change from increasing to decreasing if it goes through a critical point. So this whole region is decreasing, and we only need to choose one number to test that. And let's try a number in the left region. So what's a number we could pick over here? And say minus 2. And we're going to take that and put it into the function. So we're going to put minus 2 into the derivative. So that'll mean a minus 2 times a minus 2, and a minus 3 there. And so minus 2 times minus 2 will get us a 4. Minus 3 to get us a 1. And we don't necessarily care about the magnitude of the number. We only care about the sign. The sign is positive, which means this region here must be increasing. And so we've just answered part A. So we just answered part A, that the interval of increasing, by looking at our number line, this is literally our handwork right here. That it's increasing from minus infinity and it's increasing all the way up to minus 3/2. Now the turning point is technically considered to be constant at that. It's neither increasing or decreasing. And so the turning point does get the open interval notation. And that's our answer. This function is increasing from minus infinity to minus 3/2. And then we know it's decreasing from minus 3/2 then to positive infinity. And that's our answer then for part A. Now again, this work is to actually get to the extrema. So now putting a little bit of logical deduction here, if your function is increasing and then it's decreasing, then this minus 3/2 must be what? A minimum or a maximum? You increase to a maximum. And that's what our work is showing us. You can't decrease to a maximum. You increase to a maximum, and then you decrease away from it. And so minus 3/2 must be a local max. It's not a plateau. It's a local max. How would we know if this was a plateau? If this was a plateau, then increasing and decrease, this would stay the same. This would go from increasing to increasing or decreasing to decreasing. That would mean a plateau. But we have increasing to decreasing, which means a max. And so we identified all local extrema. There's only one critical number, and it's a local max. No local mins. So what about global? Now, this is going to be perhaps a little bit trickier when the domain isn't given to you. But if you remember some stuff about polynomials and their end behavior, remember their end behavior is dominated by the dominant term. So the dominant term in this case being minus x squared. So as this function goes off to infinities, left and right infinity, the minus sign means this is going to minus infinity. So the endpoints of the function are bending down towards minus infinity, which means there's no smallest number because it's going forever to infinity. So there's no global min. However, there is a global max. And the global max is also the minus 3/2. Now, how do you know that? Now, again, remember, all turning points are going to be at these critical numbers. The extrema are either at the endpoints. Now, the endpoints give us no global min. And then a turning point is giving us a global max. Now, of course, actually, let me just add that in there. Now, of course, you can always graph these. And here's our parabola. Here's our function we're dealing with. And you can see the end behavior is going to minus infinity. So there's no global min. That's from the end behavior, the end points. And that means then our other extrema must be the critical number. Our local extrema here, our local max, must be also then the global max, the highest point of the function. And there's our answers. So let's try another one. And so we got another polynomial, a little bit more complicated this time. And our endpoints here are, again, for a polynomial, is the domain of all real numbers. So our endpoints here are minus infinity and positive infinity. And let's just make a quick prediction about that. X to the fourth. Remember, for n behavior, the dominant term dictates n behavior. So a minus number to the fourth will be positive. So as this goes to minus infinity, this function will go to positive infinity. So positive infinity means there's no global max. Now, if we go to positive infinity, remember negative infinity will output a positive infinity here. If we put in a positive infinity, that will also output a positive infinity. So again, both the endpoints are telling us there's no global max because the function is going forever towards infinity. So we conclude that right off the bat. There's no global max. But to find the other stuff, we will need the derivative. So x to the fourth is 4x cubed. And minus 8x squared will get us a minus 16x. And the derivative of 16 is 0. And we will set this equal to 0 to find the turning points. So there's our derivative, set it equal to 0, and we will solve that. So we can factor a 4 out of this and an x. So I'll just leave that there. So you can see I factor out a 4x. And then our solutions for this, remember this is the zero product property here that we can use here. So we can set each factor equal to 0 and solve. So the first one, just divide by 4. There's our first critical number, x equals 0. Now the second one, we'll move positive 4 to the other side there. And take the square root of both sides. So the square root of 4 is 2. Now, whenever you take the square root, whenever you take a positive root, you will always have a plus or minus solution. And so we have 3 critical numbers. So now we need to go back to the function. And we need to now determine, is there a failure here? Is there a number that will cause this to fail? Well, there's no division, so we can't have division by 0. And there's no root. So we're never going to take the square root of a negative number, so there's no failure here. And so we conclude then we have a total of 3 critical numbers. And so we're going to take our critical numbers, and imagine I'm drawing this out on a piece of paper, just drawing a line. And I'm now going to write my critical numbers on this line. So we got a minus 2. And I'm just going to stick it there. And we got a 0. Remember, the purpose of the number the number line is not to look pretty. It's just work. It's our handwork. And then we have our 2 here. And then this breaks the number line into regions. So I'm going to break this into regions right at the critical numbers. And so we have 1, 2, 3, 4 regions to check. And we're going to pick a number then in a region to see what the function behavior is. So let's start with this region all the way over here. This very first region here. What's a number in this region? Well, we can choose -3. Pick simple numbers. Make your life a little bit simpler. We will choose -3 in this region to test. And we're going to put that in the derivative. Remember, our goal here is to find out if the function is increasing or decreasing. And of course, that helps us answer part A, but that also helps us determine if we're dealing with plateaus or mins or maxes. So we'll take the original function, the derivative, and we'll plug -3 into it. So we're going to have, so I'm looking right here. There's a derivative. So we got 4, plug it into -3, and we're going to make that cubed and subtract off a -16 times -3. So just plugging it in. And we would have 3 cubed is 27 minus 27. And then 27 times 4 will give us 108. And minus times minus is positive. And 16 times 3 gives us 48. And that ultimately is -60. So I do want to say again that we really don't care about the magnitude of the number. We don't care that it's 60. What we really care about is its negative. Because the negative tells us the function is sloping down in this region. And if the derivative is negative, that means the function must be decreasing in this area. So we'll go on to the next region. And we'll choose a number between -2 and 0. I mean, you could choose some -0.02835 something, but make life simple. Choose a -1. No harm here in doing something simple, simple number. And we'll plug that into the derivative. Oh, I can't paste the word to PowerPoint there. I have to rewrite that one in there. So we're plugging in a -1 into our derivative. So we're going to have 4 and a -1 cubed -16 -1. And so that's going to give us a -1 cubed is -1 times 4. And we have a +16 to give us a 12. And again, we don't care about really the value there. What we really care about is our output is positive. And if our output is positive, that means the function must be sloping up. And sloping up means it's increasing. So we'll go to the next region. 0 and +2. Well, let's take a positive one now. And we'll plug that into the derivative to see what the function is doing. So we'll have 1 cubed here, which is just 1, so we'll have a 4, and -16 to get us then a -12. And our derivative is negative, thus this region must be decreasing. And then finally we'll check the last region. And a number we can choose there, that's pretty simple, is 3. And we'll plug that into the derivative. And so we'd have 4. Whoops. messed that one all up. Cubed. And then minus 16 times 3. 3 cubed is 27. 27 times 4, I guess a positive 108 this time. And then a minus 48 to get us a positive 60 this time. And what we care about is that number is positive. The derivative is everywhere positive in this region, which means the function must be everywhere increasing. So you can see there's a lot of work here. I encourage you to use a lot of paper. Draw this all out on one big piece of paper. Even if you have to draw it sideways on your paper or the long way of your paper. No reason to try to squish everything in. So we now have our answer for part A. What is the interval that this function is increasing on? Well, it's increasing in this second interval here, this second region, and in this fourth region. So we'll just write that down in some interval notation then. So we're going from minus 2 to 0. That's increasing. And then we'll union that with 2 to infinity. And that is the interval that the function is increasing on. Minus 2 to 0, that's this region. And then 2 to infinity is this region. And then decreasing. So I'm just going to paste that one there and replug those numbers in. So decreasing. We're now in this region here. So minus infinity to minus 2. And then we'll union that with this region here, which is 0 to 2. All right, that may be a little weird. I'm back, though. I actually had a crash there. I had too many equation windows open, and it freaked out Microsoft there. So I did have to get rid of all the work here on the right side to keep the equation windows low. That's still the same thing here. And here's our answers for interval of increasing and interval of decreasing. So now we want to go to find all extrema. So again, we'll look at our work over here. And if we're going from decreasing to increasing, we decrease. Do we decrease to a max? Nope. We decrease to a min. And so minus 2 must be a local min. We increase to a max. We decrease to a min. And there's our local extrema. So our local max is at 0. And we have local mins at minus 2 and 2. So we answered the question of locals. Now remember, we started this by concluding there's no global max because the function blows up to infinity. So there's no global max. But what about a global min? Now the global min, remember, extrema, are only at turning points or endpoints. We know the endpoints go to infinity, which means the global min has to be one of the local extrema. Now, the min is certainly not the local max, So the global min is one of these two. And how do we know which? Well, we'd have to plug these into the function and see which one outputs the lowest number. So we would have to put this into the original function. And I'm just going to say this really quick because this is good to know if you're going on into math, make life a little simpler for yourself, save yourself work, is this is an even power. This is an even power, which means minus 2 and 2 will give the same output. Because the minus 2, the minus gets taken out by the even powers. So minus 2 and 2 will output the same minimum value. And so then our global min are at minus 2 and 2. And then that completes our answers. We have our intervals of increasing and decreasing, and our local mins and max, our global mins, and there's no global max. And what does that look like? Well, here's the function. This is the function we are doing right here. And let's just look. Are we increasing from minus 2 to 0? You can see the function is increasing minus 2 to 0. And it's increasing from 2 to infinity. So that looks good. We're decreasing from minus infinity to minus 2. So you can see it's decreasing right here. And then 0 to 2. So that's right here. 0 to 2, it is decreasing. Now what about our locals? Well, sure enough, here's a local max at 0. And here's a local min at minus 2 and 2. We can see the end behavior goes off to positive infinity. The end points go off to positive infinity, so there's no global max. And our global mins are these local mins then at minus 2 and 2. I do strongly encourage you to do the work first. Look at the graph last. Build your confidence in the math. And then use the picture to see if it all makes sense. Don't let the picture guide you. Do this in your brain. Understand the math and why you're doing these things. There'll be much value before you going forward. The picture help is absolutely helpful. But remember, the ultimate goal here is to learn the math. So let's try another one. And we'll get this one to be a little bit uglier looking. So, we no longer have a polynomial. So now we have this x to the 1/3 in here. And so we have to figure out the domain here. Now there's no division by 0. So we're all right there. Now we are taking a root. This is the cube root here. But remember, odd roots are okay. You can take an odd root of a square number. The cube root of minus 1 is minus 1. So odd roots, there's no problem there. It's the even roots that you can't take of a negative number. So there's no failure here. Every number works in this function, which means its domain is of all real numbers. Now I know at this point, it's probably very tempting to look at the graph to just see what the end behavior is. But how would you do this without looking at the graph? Well, remember, the domain here is all real numbers. We want to know what's happening as it goes to plus infinity and minus infinity. And that's the limit. So if we want to know how this function is behaving as it goes to minus infinity, then we take that limit. And if you recall about limit properties, the limit does pass along the factors. So we can pull off that maneuver. And if we look at this one, so as x goes to infinity, minus 4 will get crushed to nothing because the dominant term here is x squared. And a minus squared is positive. So this here is going to infinity. Now I'm being a little bit loose with the math here by putting multiply by infinity here. It's pretty loose with math there, but I'm just trying to get across the idea. This x squared minus 4 is going to infinity. Now what about this x to the 1/3? Remember the square root function forever increases. All the root functions do. Going off in positive numbers. And so this function is increasing its magnitude, but it's negative. And a cube of a negative is a negative. And so this is going off to negative infinity. And a negative times a positive will ultimately then give us a negative. So in other words, as we go to negative infinity, this function is also going to negative infinity. And what does that tell us? That tells us there's no global min. Now what about going to positive infinity? Well, it's going to be the same deal. This here will still go to positive infinity, but now this will go to also positive infinity, and that will give us a positive infinity. And what does positive infinity tell us? Positive infinity tells us there's no global max. It continues forever into the negative numbers. It continues forever into the positive numbers. So there's no global extrema. And that's from the endpoints. So let's do the work now to figure out what's happening in between the endpoints. And that's doing the derivative. So we do have a product rule here. So we're going to have x cubed, or x to the 1/3. And that's going to be times the derivative of x squared minus 4. So I am doing the product rule in my head here now. So the derivative of x squared minus 4 is 2x. Again, if you don't want to do this in your head and want to write it down, that's perfectly fine. So we have f g prime plus f prime. So now we want the derivative of x to the 1/3. X, and then 1/3 minus 1 will then give us a minus 2/3. And then this will be times x squared minus 4. And I just want to say that this is why test 2 is so important. Because I have to assume at this point you understand how to get this derivative. Because we're doing a whole bunch of other stuff now with it. So here's our derivative, product rule. we'll do what we can, clean that up a little bit. So for instance, I'll just move the 2 out here, but x to a third times x, remember you add exponents together, so this would be 3 over 3 plus 1/3 to get us a 4 over 3. And I think I'll put this back into a positive form here for the exponent. So I'm just trying to make it look a little bit nicer overall there. And that's our derivative. Definitely the ugliest one we've had so far here. And we set it equal to 0. And now we're going to solve for x. Solve for the critical numbers. So why don't we just move all this to the right side. And actually, let me just leave that as a step there so you can see it compared to the next step here. So I'm going to multiply both sides then by this denominator to get rid of the denominator on the right side here. So I'm going to multiply this by this here. So I have a 2 times or 3 times the 2. They get us a 6 there. And then multiplying both sides by x to the 2/3. So 4/3 plus 2/3 is 6/3. And 6/3 is 2. And there is technically a parentheses around that. So distributing the parentheses will get us a minus plus. Now I know this interface may be a little bit awkward. I hope you do work these out on your own with pen and paper though. And so here's our next step. Again, all I did was multiply both sides by 3x to the 2/3. That's all I did there. And we'll add minus x squared to both sides to get this 6 to be a 7. We don't need that plus sign anymore. Divide both sides by 7. And take the square root. Square root of 4 is 2. And the square root of 7 is the square root of 7. That's our best exact answer there. And whenever we take the square root, whenever we take a positive root, we will always have a plus or minus solution. And here are our first critical numbers. We have 2. So now we have to go to our derivative. And now you need to ask yourself, is there a number that causes this to fail? And the answer is yes. It's right here. If x is 0, you'll have division by 0. Now, further notice that these roots are cubed, and there's no issue with odd roots. In other words, there's no square root of a negative number here, because these are odd roots, and odd roots have no problem with negative numbers. So our only failure here is when x is 0. So let me just write that down. We have a failure at x equals 0. And now we need to check if this failure is in the domain of the original function. So we'll go to the original function. Here it is. Now recall, the domain is all real numbers, which means yes. x equals 0 is in the domain, which means x equals 0 is a critical number. So we have 3 critical numbers, plus and minus 2 over square root of 7 and 0. And so now we'll go to more hand work. Just draw a number line. We'll stick our numbers on this number line. So we're going to have a 2 over square root of 7 minus, and I'll just stick that over there somewhere. And then we'll have a 0. And then we'll have a positive. Those are our 3 critical numbers. Those 3 critical numbers divide the number line into regions. These regions are where the function is monotonic. And that means we only have to check one number in a region to know what the function's doing there. So let's check some numbers. What is a number in this region here? So square root of 7, you may not know what that is. So why don't we just say, I don't know, minus 5. Certainly minus 5 is in that region. And we're going to take minus 5. Whoops. And we're going to take minus 5 and now put it into the derivative. All right, so actually in the interest of video time, I'm just going to use a calculator here real fast to do these derivatives. So again, we're going to plug minus 5 into the derivative. And when you do that, so if you plug minus 5 into the derivative, you will get approximately, here I will use the approximate sign here, 19.5. So I did that behind the scenes with my calculator there. And this number is positive. And so that tells us then the function must be increasing in this region. The derivative is positive. The function is sloping up. So it must be increasing. So we'll go on to this next region here. And we want to choose a number in here. Now minus 2 divided by square root of 7 is about minus 0.75. So let's choose a minus half here. Or minus 0.5. That number is in this region. And if you plug that into the derivative, you will get approximately minus 1.2. So let's go to the, this derivative, I was going to go to the next region, but this derivative is negative. And so that means this region must be decreasing. Moving along to this region then, if we choose a nice symmetry here, so if we choose a positive 0.5, we will actually get this same answer again. And again, that has to do with the derivative, because the squared will take out all the negatives. This squared will also take out any negatives here, and this fourth, power 4, will also take out the negatives here. So that means there's a nice symmetry happening here. And this is negative. This derivative is negative, which means this region must be decreasing. And because of the symmetry we have here, let's choose a positive 5 all the way in this final region, because if we choose a positive 5, we will get this same answer again. And if you're not convinced of that, you can plug it into your calculator. This is a positive derivative, which means the region here must be increasing. Now, I do have a feeling that I'm on the verge of crashing again, so I am just going to get these out of the way. And let's look now at our answer for part A, the region of which the function is increasing. So it's increasing. Here's our first increasing from minus infinity to minus 2 over square root of 7. So we're increasing minus infinity to minus 2 square root of 7. And then we'll union that with the next region that's increasing way over here. So that's 2 positive 2 over square root of 7 to positive infinity. So we'll have 2 positive 2 over square root of 7 to positive infinity. And that's our region of increasing. Again, if we look at our handwork here, we have this region increasing and this region. And so what about decreasing? There is a there are mathematicians that debate about this, and because it's really not a big deal, I don't think is why it's really never been completely settled. But we see we have decreasing, decreasing. So we have these two regions that are decreasing. So the question is, can I write this as simply minus 2 over square root of 7 all the way to 2 square root of 7? Can I just do that? So in other words, is that the answer for decreasing from minus 2 over square root of 7 all the way to 2 square root of 7? After all, this all says decreasing here. And the question is 0 included? Some say yes, and some say no. For my math lab, I can't say. It's really going to depend upon who wrote the answer that day. But if you do come across this issue, you should absolutely send it to me so I can take a look at it and fix whatever may be correct. So I don't want to really get into the argument of why that is, unless you want to email me and I'll tell you more. But for now, if you have two regions next to each other that are both decreasing, just put all those together. I'm fairly confident that's overall what my math lab is going to want. And that's our answer for increasing and decreasing. So what about all extrema? Well, we know we increase to a max. We decrease to a decreasing. What does that mean? We're going from decreasing to decreasing. That means 0 is a plateau. So you only get extrema if you turn. Remember, these are turning points. Increasing to decreasing, the function turned its direction. Decreasing to decreasing means it didn't turn. And we have a plateau. And then finally we have decreasing to increasing. So you decrease to a minimum. And so we have two local extrema. So we have a local max at x equals, oh, I'm going to have to use equation editor for that one because of the square root there. And we have a local min at the positive value of that. So our local max, the minus value, our local min at the positive value. And then 0 we reject as an extrema. It's a plateau. And now remember our results for global. We did that initially when looking at the endpoints. There's no global extrema. And we're done. Here's our final answers for making my math lab happy. Let's compare that to what the actual function looks like. And here it is. So first off, let's start with our endpoints. As we go to minus infinity, as we go to the left, the function goes forever down. No global min. As we go forever to the right, the function goes forever up. No global max. How about increasing? Here we are. We're increasing from minus infinity all the way to our minus 2 over square root of 7. So that's, we figured out what this turning, we figured out where this is. It's at minus 2 over square root of 7. And then it increases again from right here, which is at positive 2 square root of 7 to positive infinity. And here's our decreasing interval right here in the middle. Now notice in this case, the plateau here is a vertical line. So that might have thrown you off when I said plateau. So again, I just want to use a simple word for you to connect to this type of phenomena here, where we have this kind of straight line that's a momentarily straight line here. And you can see this plateau here is not a turning point. It's not an extrema. And so we have our local max right here and our local min right here. And actually there is one more thing I want to say about this problem. This is our first encounter with dealing with the failure of the derivative. Remember, we check for failure because you can have a sharp corner as a turning point. But the failure doesn't guarantee a sharp corner. And that's what happened here. We had a failure at x equals 0. Now notice x equals 0 here is not a sharp corner. So our failure did not give us a sharp corner. It gave us the vertical tangent. The vertical tangent is also where the derivative will fail. And so we reject this number. I'll call the sideways plateau. But either way, it's not an extrema. So let's check out another one. And let's first deal with endpoints. So we have e to the square root of x. Now you know the square root. You can't take the square root of a negative number. Now you can take the square root of 0. Square root of 0 is 0. So x has to be greater than or equal to 0. That is our domain here. That's the domain of the function. And the domain gives us the endpoints. So our endpoints here, if you want interval notation, our endpoints here then would be 0 to infinity. So what happens at 0? Let's just check that out. We plug in 0, we will get the square root of 0, which is 0. So we get e to the 0, which is 1. Anything raised to the 0 is 1, except 0 raised to the 0 is undefined. And what about as this goes to infinity? What happens to this? So now we're dealing with infinity, which means we're going to have to take a limit. So we want to know then what happens as this goes to infinity. Well, remember the square root is a forever increasing function. It does increase slowly, but it does increase forever, which means the exponent is getting forever larger and larger, which means this is blowing up to infinity. So a number raised to a larger and larger number is going to infinity. Now, this 1 right here doesn't tell us anything yet because we don't know what the critical numbers look like. However, the infinity does tell us there's no global max then, because it's going to infinity. There's no largest number, no global max. And let me just actually separate that. So we can conclude that from the endpoints. No global max. Can't do anything with this 1 yet, though. So let's go to getting critical numbers, the derivative. So the derivative of e is always itself. And then the chain rule says multiply by the derivative of the argument. And so the derivative of square root of x would be 1/2 x to the minus 1/2. And let me just write this in a way that is a little bit more friendlier to the eyes. So I'm just going to bring this 2 here and stick it in the denominator. And I'll stick this in the denominator to make that exponent positive. And there's our derivative. Once we have our derivative, we'll set it equal to 0 and solve it. And I want to stress this again because this is a common mistake students make or forget. You can't divide to get an output of 0. The only way we can get this 0 is from the numerator. And there's no way e can output 0 either. So how would we solve this algebraically? Well, we would multiply both sides by the denominator. So that would cancel out the denominator on the left side. And of course, 0 times this will still be 0. So you're left with this. And how would you solve this? Well, you would take the log of both sides, because remember, log of e means you'll just have the argument then. But we're already at a problem because log of 0 is undefined. So what does this all mean? No solution. There is no x value that will solve this. No critical number. So let's look at the derivative again, because now we have to look for where it fails. Now we know we can't take the square root of negative numbers. We've already determined that with our domain here. However, our domain does allow 0. So the original function does allow 0, but our derivative does not. Because if you put a 0 right here, you'll get division by 0. So 0 is a failure. And so what do we do with that? Well, now we check to see if this failure is in the domain of the original function. And it is. So x equals 0 is in the original function. So x equals 0 is a critical number. So we got no critical numbers from solving the derivative. We got one critical number from failure. And that's all our critical numbers. So we'll do some handwork here with our number line. And now we only have one number to put on it. And that's 0. So that breaks the number line into 2 regions. And we just check both regions then. Now I'm going to check the right region first here, because the left region needs a little bit of explaining. Let me do the right region first. So a simple number we can choose in the right region is 1. So in this right region here, we can just choose a number 1. And we'll put it into the derivative. And what would we get? We would get e to the, we're plugging in 1, so square root of 1 is 1, so we get e to the 1 divided by 2. That's positive. Since the derivative is positive, means the function must be increasing. So what about this left region here? So now a simple choice would be to choose -1. But if we put -1 into the function, into the derivative, I should say, we have a problem. Because then we have to take the square root of -1. So there's no value here. We can't take, looking at the derivative here, plugging in -1, we can't take the square root of -1. As a matter of fact, we can't take the square root of any of these negative values here in this left region. In other words, this entire left region has nothing in it. The derivative is everywhere non-existent in this left region, because you will always be taking the square root of a negative number. So we have nothing here. And a function starts at 0 and then increases. So the question then is, well, what is 0 then? Is this, I mean, we have 0 as a critical number. Is this an extrema value? Now again, there's debate amongst individuals about this. Your book does take the position that this is an extreme value. And since you're going off increasing, remember everything to the right's increasing must mean you're coming from some minimum value. You can't start from a maximum value and then increase. That wouldn't make sense. So you start from a minimum value and you increase. Another key point here is that this domain does include 0. Remember, a closed endpoint is crucial to claim that's an extrema. And so we have for our answers for part A. On what interval is this increasing? Well, there's nothing here, and it's increasing everywhere else. Oops. So we're going from 0 to infinity. And I am choosing, again, an open interval here on the 0 because critical points are not usually chosen as being increasing or decreasing. And again, if you have this answer with my math lab but with a square bracket here, then you send that to me and I'll take care of that. Because I know there are some debates on if this is a local or not. And that it will depend upon, who wrote the answers for your My Math Lab program that day. So remember, absolutely send these to me. I mean, if you told me the interval is increasing from 0 to infinity, but you have a square bracket on one of these, I'm cool with that. As long as the square bracket's not on infinity, because that would definitely be wrong. But I know there's debate at places, and I'm willing to account for that. So make sure you send me stuff if you feel you have the right answer. And now where is this decreasing? Nowhere. It's nowhere decreasing. And then what about our extrema? We have a local min at 0. Now if we go back to the starting, we concluded there's no global max, that the function blows up to infinity. There could be, there is a global min because this doesn't exclude it. And if there is a global min, it must be at an endpoint or a turning point. And we only have one here, right here. And so this local min would also be then a global min. And there's our answers. Our interval for increasing, our interval for decreasing, and then our 4 extrema: local min, local max, global min, global max. So let's take a look at the function. And there it is. Nothing to the left. You can see it just starts right here, our global min, and then it just increases forever. So I got one more here. Trying to choose one of the end problems in the book because they're usually the most difficult. So let's check it out. So first off, let's look at the endpoints. Now, x is a polynomial, so x accepts all real numbers. Log, however, does not. Log will restrict our domain. And now, unlike the square root, you can take the square root of a negative number. You can take the square root of 0, but you can't take the log of 0. So our domain here is everything greater than 0. And if you like that in interval notation, you have 0 to infinity for our endpoints. So let's figure out then what happens at these endpoints. And to do that, we use the limit. So we want to know what's happening at this left endpoint where x is going to 0. And I want to be real loose with the math here, but as x goes to 0, that'll go to 0. Log of 0 is going to minus infinity, but minus infinity squared would be positive infinity. And you may be thinking 0 times infinity is 0, but it's not necessarily. This is an indeterminate form. And unfortunately, we won't have the tools for this until next week. So I am doing one of the last problems in the book, the harder ones. This limit is an indeterminate limit, which means you're going to really have no choice but to look at the graph. We will talk about next week how to do this limit, however. We will talk about this, but I'm going to have to leave it like this for now. And so we will have to look at the graph. And so here it is. And we can see as we go to 0 right here, this limit does turn out to be 0. Now that's by no means guaranteed. 0 times infinity can be anything. It's an indeterminate form, but we will have to look at the graph here. So we see it's 0 there. And since we're looking at the graph, we can see it also will blow up to positive infinity. So it's blowing up to positive infinity, which means no global max. So now that we've looked at our endpoints will give us a 0 and no global max. So let's look at the derivative. See what the derivative can tell us. So we're going to have to do a product chain here. So we're on x, and then times the derivative of that. So that would be 2 log x, and then the chain rule will pop out 1 over x there. So again, this is f g prime plus f prime, so the derivative of x is 1, and then the g. So that's our derivative from the product rule. And there was also a chain rule in there. And then we set this equal to 0 to solve for critical points. So let's clean this up a little bit. This x here will divide out with this x here. So we can get rid of that. And this is another this is one reason why I'm picking this problem is because of right here. And this is another common mistake that can happen is you may be very tempted right here because this has a log x and this has a log x. And say, hey, you know, why don't we just divide out a log x? Let's divide everything by log x. And if we did that, we'd be left with that. And we can solve that for x. However, you've got to be very careful when you divide out a variable with 0. So let me just do this again. Again, these x's will cancel out right here. This is not from the 0. But if we divide both sides by log x, we will have 0 divided by log x over here if we do that. And that actually eliminates a solution. So previously, if we do divide by log x, we get this. And this here will only give us one answer. And since we're already showing the graph here, you can clearly see the graph has 2 turning points. But if you divide by log x here, you will only find one of them. It's always dangerous to divide out a variable with 0 because you risk losing a solution. So if you divided by log x here, you'd get stuck. You'd be like, wait a minute, I see 2 turning points, but I can only get 1. And you want to avoid using 0 to divide out a variable. You want to avoid that unless you're really certain you know what you're doing. So what we're going to do here is we're going to factor out the log x. We're going to factor it out. We're not going to divide it away. We're just going to factor it out. Like that. And now we can use the 0 product property to get both solutions. So another good thing to know about log is that the log of 1 is always 0. No matter what your base is, log of 1 is always 0. But if you didn't know that, how would you solve this? Well, to get rid of a natural log, you have to raise it from base e, both sides. And then e to the natural log simplifies to just the argument. And then anything raised to 0, except 0, equals 1. 0 raised to the 0 is another indeterminate form. Actually, 0 raised to the 0 is undefined, now that I think about it. 0 raised to the 0. Even in math, nothing raised to nothing can't get something out of that. So that's what we get for our first one, x equals 1. And solving this next one then, we'll just move the 2 to the right side, make it minus 2. And then we'll raise both sides from e. And we have our answers. Now, since we have pulled up the graph here, because we couldn't do this limit right here. We will be able to next week, though. But you can see now that e to the minus 2, well, that must be right here. That must be this one. Because you can clearly see that 1 is this one. So for our intervals of increasing, we can see we're increasing from 0 to e to the minus 2. And we are also increasing from 1 to infinity. And what about decreasing? Well, since we got the graph already pulled up, we'll just look. We're decreasing in this one interval here from this local max to this local min. And so that's from e to the minus 2 to 1. And then what about local extrema? Well, we have a local min at this end point, because this is a it is not closed. Ooh, almost caught myself there. This endpoint is not closed. Thus, it can't be extrema. So this is not an extrema here because it's an open endpoint. So our only local min is at 1. And then we have our local max right here at what we figured out is e to the minus 2. Now we concluded there's no global max because this goes off to infinity. And now what about a global min? Now remember, this 0 is an open interval. Open intervals cannot be extrema. So our global min is right here at this 1. And there's our answers. So kind of a cool looking function. A little bit unfortunate that we couldn't do this limit here. And I do want to be clear, 0 times infinity is indeterminate. It does turn out in this case, though, that it is 0. We will talk about this next week, though, because we need L'Hopital's rule to do that one. So here it is. This will conclude, then, Extrema, and we will use this to do word problems. So this is my last point I want to make here about where we're going, and I hope where you get to, is that notice doing the derivative is just one step. So everything you've done on your homework and working up to test 2, all you were doing there was doing one derivative. Now that one derivative is just one step in our problems. And that's why I was trying to stress how important it is that you can get under your belt how to do derivatives, because they're now going to be just a step in our work. And everything we're doing here will get more complicated when we apply it to word problems then. So if you made it over test 2, I think you're in a strong position to finish the semester off. But be prepared. Test 3, this material is without doubt going to be the hardest. But I promise you, test 4 will then be easier. And it's not because of me or anything. It's a matter of the material. So test 3 will be challenging. Get your brain prepared and really try to get Extrema under your belt so that when we apply this to word problems, you won't struggle as much with trying to get the Extrema. And I will talk to you in the next video.